Okay, so in this video, we're going to go ahead and talk a little bit about energy, what it is, and kind of where it comes from. So, energy is sort of the counterpart to matter. So, matter is the stuff. Remember, it matters anything that has volume and mass, whereas energy is kind of the stuff that makes it go. So, matter is like what it is. Energy kind of helps transform or do something or change what's happening somehow. So, energy is the capacity to do work, therefore. So we got to kind of do a couple of nested definitions here. So, what do I mean by work? Work is the result of a force acting on a distance. So, you might think about it takes some work to like push a book across the desk, or like I was mad about the amount of work it took me to get up the stairs with how heavy my backpack was today. So, it's a lot. It's something that you have to, it's the result of a force acting on a distance, and it's going to, kind of like, it's like, if you think about it, it might be kind of like effort. But what do I mean by force in the end? Well, a force is a push or pull on an object as a result of it kind of interacting somehow with its surroundings, whether that be like gravity, magnetism, friction, electrostatic forces like positive and negative charges in ions, that kind of a thing. Like with matter, we also have the law of conservation of energy. So, energy, like matter, is neither created nor destroyed in chemical reactions. So, this is the law of conservation of energy. So, the total energy in a system is constant. So, energy can be kind of transferred or transformed between different types of objects or from one object to another. But it doesn't come from nothing, and it doesn't simply mysteriously disappear. It's just transformed. So, the two main types of energy we're going to talk about throughout class, so everything can kind of be distilled down into these two types of energy. So those would be kinetic energy and potential energy. So kinetic energy is going to be the energy we associate with motion. So it's kind of really what I guess in my head I traditionally think of as energy, that movement kind of a deal. So airplanes have a ton of kinetic energy because they're huge and it's a lot of mass and it's moving very fast. So it's a lot of like energy of motion there. And the kind of contrasting type of energy is potential energy. So it's the energy associated with position or composition. So it's based upon kind of the location of the object or what the object is made of. So this is the potential to do work, like the opportunity for something to happen there. It's stored energy. So it could be moving, but it's not moving just yet, but it like has the possibility to have this energy of motion. And specifically, chemical molecules have potential energy stored in the chemical bonds that hold them together. So that'll be often where we talk about potential energy in this class. If you check out this picture over here, where we're looking at the drawing of the dam, we can see that as the water is being held back, so we'd think the water naturally would want to keep flowing down the river. The dam is stopping that water from flowing down the river. So it's kind of like keeping it from happening. It's stopping that motion. So we have a high amount of potential energy built up on the far side of the dam, holding the water up. That position, it's holding it up against gravity. Gravity wants to pull that water down to the other side of the dam. So we have a high amount of potential energy over here on this side of the dam, whereas when we're on the far side of the dam, when we're where the like natural riverbed sets, for example, it's got a low potential energy because it's closer to the ground, so that it's letting gravity act on it. It's staying down, whereas the dam is stopping that gravity from acting, so it's kind of fighting against it, and that's kind of storing the energy in a way. So as we're going to increase our height here to hold that water back to get that height up, we're going to increase the amount of potential energy. So when we're talking about kinetic and potential energy in any system, so whenever we're considering the amount of energy having to do with a certain set of objects, the total amount of energy in the system is going to be the sum of the kinetic energy and the potential energy. So total energy is all of the kinetic energy plus all of the potential energy. Pretty easy, right? So you can always transform your energy. So you can go from like potential energy, we can make it kinetic energy, we can go back to potential energy, but you never really gain or lose energy in your system. So, we can stop that water from flowing down, we can push it back up, but we're still going to have the same amount of energy in our system. that's the application of the law of conservation of energy here. So systems with high potential energy often want to try to convert that potential energy to kinetic energy. So they want to move to a state where they have low potential energy or a lower potential energy. So, you think about it, the water wants to rush past that dam. So if it has the opportunity, if there's a crack and it's putting pressure on it, it's going to do everything that it can to continue want to rush down that river, to let gravity act upon it. So systems would rather expend the potential energy as kinetic energy than hold on to it. You have to put energy in to raise your potential energy, and then you expend energy as kinetic energy to lower the potential energy. So we might talk about a couple more specific types of energy. So we broadly classify energy as kinetic and potential, but we have a couple of other kinds that we would like to talk about as well. This might be electrical energy. So this would be the energy associated with the flow of electrical charge. So when you're charging a battery, you're adding energy into the system. So therefore, the potential energy when you're charging the battery is increasing, whereas when you're like actually using an electric current to run a light or something, that's going to be kinetic energy, because you've got an electric current kind of flowing and moving. When we're talking about thermal energy, that's going to be the energy associated with like the random motion of particles. So anything having to do with kind of that wiggle we talked about with our solids, right? And our liquids are moving and our gases are always flying around. So that's the kind of random motion of particles we're thinking about here. So again, it's a form of kinetic energy because it's associated specifically with the motion of the particles. We'll get into a more precise definition of thermal energy, and we're going to talk a lot about it towards the end of the chapter here. But it's worth talking about in terms of it being specifically a kinetic energy here. So we also have chemical energy. Ding, ding, ding. That's probably going to be one that's important to us, right? So it's going to be the energy associated with the position of atoms in a molecule. So we talked about potential energy having to do with either position or composition. This is the composition portion. So energy is stored in chemical bonds as potential energy. So those different types of bonds hold different amounts of energy. And so however your molecule is arranged, whatever kinds of bonds it has and where those bonds are located are going to determine the amount of chemical energy stored in your molecule. So when we break a molecule apart, we're going to have to transform some of that energy so that we can lower the potential energy. So if you rearrange molecules and you take those atoms, you put them into a different arrangement, like let's say when we were burning butane and oxygen and we were turning them into carbon dioxide and water, for example. We rearranged the butane and the oxygen. We broke those apart. We rearranged our atoms, and those became the carbon dioxide and the water. So that's kind of how we can change the lower the potential energy of the system. So we also have some units that are associated with energy. So I'm just going to point them out to you here. We'll kind of continue to use them and talk about them, but I don't really want to dwell on them. I'll always give you these conversion factors if we need them. So the one that you may have seen here before, or I guess you may have seen two here before. Duh, we eat food. But you may have seen kilowatt hours before. This is how we measure energy when it comes into our house. So if you pay the power bill, they usually tell you, you owe this much for this many kilowatt hours. This is how much you used. Also, that calorie that's written in the second row here with a capital C. So the distinction is made of a capital C calorie and a lower C calorie. So a lower C calorie is worth this many joules. We'll talk about joules in a little later on in chapter 3, but 1 calorie is actually 4.184 joules. However, if we look down here at this equivalence, we have 1 calorie with a capital C equals 1,000 calories with a little c. So that capitalization does matter here. Remember, we talk about that quite often when we're writing units. Capitalization matters. So basically, a capital C calorie is a kilocalorie of the lowercase c calories. So This is just a nice equivalence to know. So when you actually read your food label, we're looking at kilocalories. So we're looking at 1,000 calories. So if you tack on a couple zeros, that's actually how many calories you're eating. But it's not really useful for us to measure it that way or display it that way. So again, we're kind of hiding our zeros in our unit there, like we talked about before. So I have a slide here just to show you a little bit about how these units scale when we're looking at things. So we'll talk about this a little bit later on in chapter 3 as well. This is a useful measurement that we use, or this is a useful kind of property of matter that we tend to use to compare the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So we might test this measurement out with different substances. But in this case, we're just looking at what it takes to raise, like how much energy does it take to raise 1 gram of water by 1 degree Celsius? Well, in this case, it takes 4.18 joules. It takes 1 calorie. Oops. It takes 0.001 calories with a capital C. And then you can see that it's an even teeny tinier number compared to that with our scientific notation when we're looking at it in kilowatt hours. It's 10 to the minus 6. If you wanted to run a 100-watt light bulb for an hour, this is how much energy it would take of each of our different values. So it would be a lot of joules. It would be a lot of lowercase c calories. It would be 86 capital C calories, and then just like 0.1 kilowatt hours. So that way you can kind of compare the scales. You can kind of get a feel for what those units mean. So that was just a little bit here about kind of what energy is, how we're going to use it, and how we have that going on.